September 28, 2008. A rocket no bigger than a telephone pole reaches orbit for the first time. This isn't NASA. It's not Russia. It's a startup called SpaceX, and they're down to their last attempt. Meet Falcon 1, the rocket that almost never was. In 2002, Elon Musk founded SpaceX with a radical idea: make rockets reusable, like airplanes. But first, they needed to prove they could reach space at all. Falcon 1 was the testbed, a two-stage rocket standing just 70 feet tall, powered by a single Merlin engine, burning RP-1 kerosene and liquid oxygen. Here's what made it different. Traditional rockets were expendable, costing hundreds of millions per launch. Falcon 1 aimed to slash that cost by designing for mass production and simplicity. The Merlin engine used a gas generator cycle, cheaper than the complex stage combustion systems of its competitors. But simple doesn't mean easy. Flight 1 in 2006, engine fire 33 seconds in. Flight 2 in 2007, stage separation failure. Flight 3 in 2008, first stage collides with second stage, 3 failures. SpaceX was nearly bankrupt. Then came Flight 4. On their final funded attempt, Falcon 1 delivered a dummy payload to orbit, the first privately developed liquid fuel rocket to do so. Flight 5 followed 2 months later, proving it wasn't luck. Falcon 1 never flew again. By 2009, SpaceX shifted focus to its bigger sibling, Falcon 9. But the lessons were priceless. The Merlin engine, it powers every SpaceX rocket today, evolved but fundamentally the same. The vertical integration, now standard practice. Falcon 1 wasn't just a rocket. It was proof that a private company could challenge governments in space. Without it, there's no Falcon 9, no Dragon capsule, no Starship. Every revolution starts small. This was SpaceX's patient zero. The Falcon 9 has landed over 200 times. Think about that. A rocket that goes to space, then flies itself back to Earth like a sci-fi movie. Except it's real, and it happens almost weekly. This is the machine that rewrote the economics of spaceflight. Here's how it works. Falcon 9 stands 70 meters tall. It's a two-stage rocket. The first stage, the booster, does the heavy lifting. 9 Merlin engines generate 764 tons of thrust at liftoff. That's enough to hoist a fully loaded 737 into orbit. The second stage has a single Merlin engine optimized for the vacuum of space. It carries the payload, whether that's satellites, cargo for the space station, or astronauts in a Dragon capsule. But here's where it gets revolutionary. After separation, the first stage doesn't just fall into the ocean. It flips around. Cold gas thrusters orient it. Grid fins steer it through re-entry. Then those same 9 engines reignite for a controlled descent. It lands vertically on a drone ship in the Atlantic or back at the launch site. Precision touchdown within meters. The entire booster can be reflown in weeks, not years. Some boosters have flown over 20 times. This is why launch costs dropped by 70%. Reusability was once impossible. Engineers said the forces were too extreme, the engineering too complex. SpaceX proved them wrong through relentless iteration. Falcon 9 has launched over 250 times. It's deployed thousands of Starlink satellites. It's delivered humans to orbit. It's become the workhorse of the commercial space age. And it's just the beginning. Because reusability isn't just about saving money, it's about access. When rockets can fly like airplanes, space stops being a destination for governments and becomes infrastructure for humanity. Falcon 9 didn't just land. It opened the door. 3 rocket cores ignite simultaneously. Over 5 million pounds of thrust erupt from 27 Merlin engines. This is Falcon Heavy, and it's the most powerful operational rocket on Earth. But here's the paradox. It's built from recycled parts. Let's break down how SpaceX turned scrap into orbital supremacy. Falcon Heavy isn't a new design. It's 3 Falcon 9 boosters strapped together, arranged in a configuration engineers call an asparagus staging system. The 2 side boosters are literally refurbished first stages from previous missions. They've flown before. They'll fly again. The center core takes the brunt of the load. During ascent, all 3 cores burn together until the side boosters separate at 2.5 minutes. They flip around, reignite their engines, and land vertically back on Earth. Meanwhile, the center core continues pushing the payload towards space before attempting its own landing on a drone ship in the Atlantic. The engineering elegance is deceptive. Synchronizing 27 engines is extraordinarily complex. The acoustic vibrations alone can shatter components. The structural loads at max aerodynamic pressure could tear lesser rockets apart. SpaceX solved this through iterative testing and vertical integration. They manufacture 80% of components in-house, which means faster troubleshooting. Now the implications. Falcon Heavy can deliver 64 metric tons to low Earth orbit for $90 million per launch. That's half the cost of comparable systems. It opens possibilities for crewed lunar missions, Mars cargo runs, and direct geostationary insertion of heavy satellites. We're not just reusing rockets, we're fundamentally restructuring space economics. The barrier to entry is collapsing. What was impossible a decade ago is now routine. Falcon Heavy proves that audacious engineering combined with relentless cost optimization can democratize access to space. The future isn't about building bigger rockets, it's about building smarter ones. Right now, a spacecraft built by a private company is docked to the International Space Station with 4 astronauts inside. That spacecraft? The Dragon capsule. And it represents something unprecedented in spaceflight history. For the first time ever, humans are routinely traveling to orbit in a vehicle not owned by a government. But here's the paradox. Dragon wasn't supposed to carry people at all. Let's break this down. Dragon began in 2006 as a cargo vehicle. NASA needed a delivery truck after retiring the space shuttle. SpaceX won the contract with a simple cone-shaped capsule. Version 1, called Dragon 1, flew 23 missions between 2010 and 2020. It hauled supplies, experiments, even mice to the ISS. But it had a critical limitation. It splashed down in the ocean, making refurbishment expensive and time-consuming. Enter Dragon 2. SpaceX split this into 2 variants, Cargo Dragon 2 and Crew Dragon. The upgrades were radical: sleeker aerodynamics, touchscreen controls replacing hundreds of physical buttons. Most importantly, 8 Super Draco engines built directly into the hull. These thrusters can produce 16,000 pounds of force each, enabling a launch escape system. If the rocket fails, Dragon can blast away to safety in milliseconds. Crew Dragon became the first private spacecraft to carry astronauts in May 2020. Since then, it's flown over 40 people to orbit. NASA astronauts, private citizens, international partners. But here's what changes everything. Dragon isn't disposable. Each capsule can fly up to 5 missions. That reusability drops costs from $200 million per seat on the space shuttle to roughly $55 million on Dragon. We're not just going to space more affordably, we're industrializing orbit. And Dragon is the workhorse making it possible. Before SpaceX landed rockets on floating platforms, there was a strange tower in Texas that hopped like an insect. Meet Grasshopper, the prototype that proved everyone wrong. In 2012, the aerospace industry believed reusable rockets were science fiction. Throwing away million-dollar hardware after one use was just how it worked. Elon Musk disagreed. Grasshopper was SpaceX's answer, a 10-story test vehicle built from a Falcon 9 first stage. It had a single Merlin 1D engine, 4 steel landing legs, and 1 mission: prove controlled vertical takeoff and landing was possible. The physics seemed impossible. A rocket is essentially a controlled explosion. Landing one requires throttling the engine with surgical precision. Too much thrust and you fly back up, too little and you crater. The margin for error is razor thin. Between 2012 and 2013, Grasshopper completed 8 test flights, each one higher than the last. The final flight reached 744 meters. It hovered, translated sideways, then descended perfectly onto its launch pad, the same vehicle, 8 times. The data from Grasshopper fed directly into Falcon 9's landing algorithm. Every oscillation, every thrust adjustment, every successful touchdown taught the system how to stick the landing. 3 years later, Falcon 9 landed at Cape Canaveral, the sonic boom heard around the world. That landing saved approximately $60 million in hardware costs. Today, SpaceX has landed over 250 boosters. Grasshopper retired in 2013, but its legacy rewrote the economics of spaceflight. It proved that the most important breakthroughs often look absurd at first. A rocket that hops. Now that's the future landing. May 5th, 2021. A 160-foot steel tower ignites 3 Raptor engines and climbs 6 miles into the Texas sky. Then it does something no Starship prototype had ever done before. It lands and survives. This is SN-15, the breakthrough. 4 previous prototypes tried. SN-8 belly flopped perfectly but hit the ground too hard. SN-9's engine failed to relight. SN-10 actually landed, then exploded 8 minutes later from a methane leak. SN-11 never made it down at all, disintegrating mid-descent in thick fog. The pattern was clear. SpaceX could launch. But landing a skyscraper-sized rocket was proving brutally difficult. SN-15 changed everything because SpaceX changed everything. They upgraded the avionics, reinforced the structure, redesigned the Raptor engine plumbing to prevent leaks, and crucially, they improved the flight computer's ability to manage the belly flop maneuver, that horizontal descent where the rocket uses its body as an air brake before flipping vertical for landing. The flight itself was textbook. Ascent on 3 engines, engine cutoff at apogee, the controlled fall, then the flip. 2 Raptors reignited. The rocket descended through its own exhaust plume, landing legs deployed. Touchdown. A small fire ignited at the base, but SN-15 stood firm. Why does this matter? Because SN-15 proved the flight profile works. This isn't a capsule with parachutes. This is a fully reusable spacecraft designed to carry 100 people to Mars. The belly flop maneuver is essential because it allows atmospheric braking without heavy heat shields. SN-15 never flew again. It didn't need to. It validated the design and paved the way for SN-20 and beyond. The prototypes that followed would be taller, more powerful, and paired with the Super Heavy booster. But they all owe their existence to the first Starship that stuck the landing. SN-15 didn't just survive. It proved reusability at scale was possible. Picture this, a rocket booster with 33 engines. Not 3, not 13. 33 Raptor engines igniting simultaneously, producing over 16 million pounds of thrust. That is the Super Heavy booster, and it is the most powerful rocket stage ever built. To put that in perspective, the Saturn V that took humans to the moon had 5 engines on its first stage. Super Heavy has more than 6 times that number. Why? Because it needs to lift Starship, the fully reusable spacecraft designed to carry up to 100 tons to orbit, or eventually, to Mars. Here's where it gets interesting. Traditional rockets are expendable. You use them once, then they crash into the ocean. Super Heavy changes that equation entirely. After separating from Starship at around 70 kilometers altitude, it performs a boost-back burn, flips itself around mid-flight, and returns to the launch site. The goal? To be caught by giant mechanical arms called chopsticks on the launch tower itself. No landing legs, no barge in the ocean, just precision engineering catching a 20-story booster out of the sky. SpaceX first attempted this in October 2024 and succeeded. The booster descended, fired its engines to hover, and was grabbed midair. It sounds like science fiction, but it is operational reality. The implications are staggering. Reusability slashes costs. It transforms space access from a rare, expensive event into something routine. Super Heavy is not just a booster. It is the foundation of a transportation system designed to make humanity multiplanetary. And that shift from expendable to reusable, from earthbound to interplanetary, begins with those 33 engines firing in unison. SpaceX just doubled the payload capacity of the world's most powerful rocket, and almost nobody noticed. Starship version 2 isn't just an upgrade. It's a fundamental redesign of how we think about interplanetary transport. The original Starship could carry 100 tons to low Earth orbit. Version 2, 200 tons. That's the equivalent of launching 2 Boeing 737s worth of cargo in a single flight. But here's the paradox. The rocket isn't bigger. So how did SpaceX double the capacity without adding size? The answer lies in 3 critical innovations. First, the propellant tanks. V2 uses a stretched upper stage, adding 9 meters of length exclusively for fuel. More fuel means more delta V, the physics term for changing velocity in space. Second, the Raptor 3 engine. Each new engine produces 280 tons of thrust, a 30% increase over Raptor 2. 6 of these engines now power the ship instead of the original configuration. Third, structural mass reduction. SpaceX shaved off multiple tons by switching to thinner steel in non-critical areas and optimizing the heat shield tile placement. Every kilogram saved in structure is a kilogram available for payload. But why does this matter? Consider Mars colonization. The original plan required multiple Starship launches to assemble enough fuel and cargo in orbit for a single Mars mission. Version 2 cuts that number in half. Fewer launches mean lower costs, faster timelines, and reduced risk. NASA's Artemis program is watching closely. The lunar variant of V2 will carry habitats, rovers, and life support systems in single trips. This isn't incremental progress. This is exponential capability growth. Starship V2 transforms space logistics from a bottleneck into a highway. The era of mass space infrastructure just became inevitable.